Let's sketch a hyperboloid of two sheets centered at the origin. An equation that describes a hyperbola of two sheets centered at the origin is given by the following quadratic equation: minus x squared over a squared minus y squared over b squared plus z squared over c squared is equal to 1. This is different than the hyperboloid of one sheet that we've discussed previously. The hyperboloid of one sheet centered at the origin is given by the equation x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. Notice that these two equations look similar, but they differ by a minus sign essentially. We have minuses in front of both the x and y terms in the hyperboloid of two sheets, and only a minus sign in front of the z term in the hyperboloid of one sheet. Now, these two equations would describe different surfaces, but each of these surfaces would have a central axis that is parallel to the z-axis. So for the hyperboloid of one sheet, as we've seen similarly, that's going to be a surface that looks roughly like this. Kind of looks like cooling towers of a nuclear power station. While we're going to see today that a hyperboloid of two sheets will look something similar to this. The hyperboloid of one sheet has just one continuous surface, while the hyperboloid of two sheets has two surfaces. For now, we're going to sketch a hyperboloid of two sheets given the equation we have. Let's rewrite our equation for a hyperboloid of two sheets. It is minus x squared over a squared minus y squared over b squared plus z squared over c squared is equal to 1. Well, I don't like dealing with so many minus signs. Let's draw our rectangular coordinate system. And let's begin with the YZ trace. The YZ trace is going to be drawn by taking the line of intersection between a plane that is parallel to the YZ plane, and that plane has a normal vector that is parallel to the x-axis. An equation of the plane that would help us draw the YZ trace would be the equation x equals 0. Therefore, let's put x equals 0 into our quadratic equation. When we do that, we end up with the equation z squared over c squared minus y squared over b squared is equal to 1. Notice that this is a hyperbola in the YZ plane. If you remember how to sketch hyperbolas from our second semester calculus class, what you would do with this information is you would create a rectangular box. The rectangular box would have a z coordinate at c and minus c, and a y coordinate of b and minus b. You would then create diagonal lines going through opposite corners of this rectangular box. Now I'm doing all of this dotted because these dotted lines are not going to be part of our final graph. They're just helping guide my sketch because these are some of the tools I learned in my second semester calculus class. Now that we have this, notice because z appears first, the transverse axis will be along the z-axis, or at least rather, I might have called that wrong. I'm not sure if it's called the transverse axis, but I know the axis along which our hyperbola is going to be centered about is the z-axis because z appears before y and there's a minus sign in there. That's what I remember from my second semester calculus class. With that said, I'm going to draw the two curves of this hyperbola in the YZ plane, and those two curves will look something like that, where those diagonal lines are asymptotes in which our curves approach. Great, so we now have the YZ trace. If you do any other value for x, you're going to get different traces that would still all be hyperbolas. Now let's do the second trace that I often like to do. I often like to do a trace that is constructed from a plane that is parallel to the xy plane. So this trace will be the xy trace, and that trace is formed from the line of intersection of a plane that's parallel to the xy plane and our surface. That plane that is parallel to the xy plane has a normal vector that is in the positive z direction. So our xy trace is found by taking the plane described by the equation z equals 0 and intersecting our shape. So let's see, let's intersect our shape at z equals 0. I'm going to just draw my plane. Here's our plane. We're going to do z equals 0. So I'm going to put that plane right in the xy plane. And let's see what that would look like. So I am going to, since we have z equals 0, I'm going to plug that into our equation. Our equation of the quadratic surface is minus x squared over a squared minus y squared over b squared is equal to 1. Well, let's just go ahead and distribute. Let's multiply that 1 by, let me rephrase that. Let's go ahead and multiply everything by the minus 1. So we have x squared over a squared plus y squared over b squared is equal to minus 1. Is that a shape? Would that produce a graph that we recognize? There's something bothering me about this. There's this minus 1. This minus sign is bothersome. We're not going to be able to construct a graph in this real space because of that minus sign. And here's why, just really quickly. Let's go ahead and try to express y in terms of x. If we try to express y in terms of x, we're going to isolate y on one side of the equal sign. We will multiply through by the b squared, and I'm going to factor out the minus sign from both of those terms. Take the square root of both sides, and notice we end up with an imaginary number underneath the square root. It's imaginary. I know it's imaginary because this is a positive quantity, because any value of x squared is going to be positive. Any value of a squared will be positive. 1 is a positive number. B is a positive number. We have this minus sign underneath the square root. this is an imaginary result, an imaginary solution, and we can't plot that imaginary solution in real space. Therefore, the XY trace tells us nothing. It's imaginary. What that means for us is that our shape isn't going to exist there. So we're going to have to find another value for Z that might work. And the main thing is we have to make sure that we have an expression that we can evaluate. So let's try again. We know Z equals 0 doesn't work. I'll just X that out. That trace doesn't work. Let's copy to this page. Let's try another trace. Let's make Z equal to C. Let's see what we get there at Z equals C. Now we see from our sketch here that that's going to be the vertex of our hyperbola in the ZY plane. So if Z equals C, we have minus x squared over a squared minus y squared over b squared plus c squared over c squared is equal to 1. C squared over c squared is 1. This ends up being minus x squared over a squared minus y squared over b squared plus 1 equals 1. We end up with y squared over b squared equals minus x squared over a squared when we do the algebra for that. Well, unfortunately, we kind of have the same problem here, but it's a little bit better. The problem is we have, if we just solve both sides for y, we get plus or minus b over a times the square root of minus x squared, which is just plus or minus b over a, absolute value of x, and again we have an imaginary number because we have a negative sign underneath the square root. There is one and only one situation in which we could sketch the result of this equation. And that situation occurs when x equals 0. Well, when x equals 0, then y equals 0. Oh, so x equals 0, y equals 0? That's the condition for us to find the Z intercept. So this is going to tell us potentially that our sketch, our graph of this quadratic surface, intercepts the z-axis. So let's find that z-intercept. That z-intercept occurs when x equals 0, y equals 0. So plugging that into our equation, we get z squared over c squared is equal to 1. This means that our z-intercepts are at the values of plus or minus c. Let's look at our sketch. Notice the hyperbolas intersect the z-axis at c and minus c. What we have found then is this must be two different vertices of our hyperboloid. And we found this by taking the z equals c plane. That plane intersects our surface at z equals c, and that produces a point. That produces a vertex. And we could take our z equals minus c plane, intersects our surface at z equals minus c, producing the other vertex. And those vertices are just points. Okay, well, z equals 0 told us nothing, but z equals c tells us more information. Well, what if we take another plane? Let's take our plane maybe up here somewhere. We'll call that value arbitrarily. We'll just call that value z naught. So we're going to find the z equals z naught trace. That z equals z naught trace looks like, at least the equation looks like, minus x squared over a squared minus y squared over b squared plus z naught squared over c squared is equal to 1. Let's rearrange this equation. I'm going to rearrange it by multiplying everything by a minus 1. And let's move the z term to the other side of the equality, since we are treating this z equals to z naught as a constant. Okay, well, let's take a look at this. Here we have something that is very reminiscent of an ellipse. We would get an ellipse only if this right side is a value greater than 0. We could potentially get a point if this value is equal to 0. Let's determine what z naught needs to be in order for us to get a number greater than or equal to 0. Because if we get a number greater than or equal to 0 on the right side of this expression, then I know the xy trace is going to be a trace of an ellipse depending on the value of z. So to determine this, let's just solve for z naught. We have z naught squared is equal to 1, and actually this should be greater than or equal to 0, which means then that z naught squared is greater than or equal to c squared. If we take the square root of both sides, we end up with the inequality. Minus c is less than or equal to z naught, which is less than or equal to c. Put another way, z naught has to be a value greater than or equal to c, or a value less than or equal to minus c. So if c naught is a value greater than or equal to c, let's try that. Let's go to the next page. Let's let z be a value greater than c. We know if z is a value equals to c, we get a vertex. So if z is a value greater than c, well, let's come up here. Let's take our plane and let's do some value up here. From the previous page, we have x squared over a squared plus y squared over b squared is equal to z naught squared over c squared minus 1. And if z naught is a value greater than c, then this quantity is a value greater than 0. And if that quantity is a value greater than 0, let's just call it something. Let's call that quantity d squared. How's that? So we have x squared over a squared plus y squared over b squared is equal to d squared. Now the reason why I called it d squared, because if we divide both sides by that d squared, we get x squared over ad quantity squared plus y squared over bd quantity squared is equal to 1. Now you're able to see why I called that quantity on the right side d squared, because in calling it d squared, it makes it easier to recognize that this is an equation of an ellipse. And if we were to project this equation onto the xy plane, so let's look down on our coordinate system, down from the positive z-axis. If we were to project this onto the xy plane, we would have an ellipse where our ellipse would intercept the xy axes along the y-axis. This would be BD and minus BD. Along the x-axis, this would be AD and minus AD. The point being, we have an ellipse, and depending on the value of D, that ellipse would grow in size. We could have bigger ellipses or smaller ellipses, depending on what D is. If D were equal to 1, for example, this would just end up being an ellipse with sides or with axes of A and B. So now that we know that that describes an ellipse, let's add that to our sketch. The traces drawn by letting Z be greater than C ends up with ellipses. And notice we get like a shallow looking bowl there. This shallow looking bowl is one of the sheets of our hyperboloid of 2 sheets. Now you might have guessed that this Z not greater than C also applies for Z not less than minus C. And that's because the Z naught is squared. This is good for both plus or minus C. So we would have the same ellipsis down below. Describing our hyperboloid of 2 sheets. So to clean this up a little bit, a hyperboloid of 2 sheets look like 2 cups. 1 cup held up, 1 cup held down, and this hyperboloid of 2 sheets is centered along the z-axis in our x, y, and z rectangular coordinate system, where this quantity right here was c, this was minus c, and again, our equation for this hyperboloid of 2 sheets is minus x squared over a squared, minus y squared over b squared, plus z squared over c squared is equal to 1.